Hello again, physics friends. Today we are going to see how you calculate the rotational inertia of an extended body, and we'll start with an example of a hoop. Okay, I guess that was purple. The hoop, basically, it's like a Wellesley hoop, right? Like so. It's a three-dimensional object, and we can treat it like a two-dimensional object, though. If we look at it from above, we'll treat it as a thin ring, okay? Let's recall the definition for point particles of the rotational inertia. So we called I the rotational inertia. And for a collection of point particles, we said that the rotational inertia was the perpendicular distance squared between the object and the rotation axis multiplied by the mass of that object summed up over all particles. But what if you had an extended object with a rotation axis, say here, and you had, you don't have a collection of point particles? Well, you can imagine breaking up the extended object into a collection of point particles, each with a perpendicular distance and each with a chunk of mass. We could call it dm. And you could integrate over the whole object to get the total rotational inertia. And indeed, the rotational inertia for the extended object can be written as the integral of r perpendicular squared for each little mass element dm. So how does that play out in the case of the hoop? Well, actually, we kind of know the answer already for the hoop, because every mass on this hoop, every little piece of mass on this hoop is the same distance from the center. And let's be clear here, we're talking about a hoop that's rotating about an axis that goes through the middle of the hoop. So in the 3D case, it would look something like this. There'd be an axis right through the middle of the hoop, and the hoop would be rotating about that axis. So here, the sense of the rotation might be counterclockwise, and the axis would be a line through that purple point perpendicular to the page. In that case, every single little chunk of mass is an equal distance, capital R, away from the center. And we can say that the total mass of this hoop is capital M. And in that case, once you add up all of those little elements, the total rotational inertia will just be mr squared. But let's see how that works out if we wanted to explicitly do the integral. So for this, let's consider a small chunk of mass, which I'll highlight in green, just this little stretch of mass right here. Okay. That little stretch of mass has a length, which I'll call ds. S is like a little arc length, and ds is a little infinitesimally short arc length. And there's a mass associated with that length. Okay. So we're going to integrate all of those mass elements over the entire hoop. Okay. So how do we write down dm, the mass of that little element? Okay. Well, if we knew the linear density of the material and multiplied it by the length ds, that would tell us the mass. What is this lambda? It's the total mass of the hoop divided by the total perimeter of the hoop, 2 pi r, and it's a constant. Right? It'd be like the density of the material. Okay. How do we express ds? In terms of some, let's say, angle. We can call this little chunk of angle, this little differential angle, d theta, and we know that the radius of the circle is r, and so we know that the arc length ds is equal to r d theta. So when all is said and done, we can express dm in terms of these quantities, m and r and d theta. So it's lambda ds. Lambda is m over 2 pi r, and ds is r d theta. So our dm is then m over 2 pi times d theta. Simple as that. Okay, so we can now bring that in over to our integral. We have integral of r perpendicular squared, which we'll leave alone for now. And then instead of dm, we can write m over 2 pi d theta. The m and 2 pi are constants, so we factor those out. What is this r perpendicular? Well, that's the perpendicular distance from our mass element of interest to the center, the axis of rotation. Right, so it's the perpendicular distance from here to the rotation axis. Well, that is just capital R, which is a constant. So we'll take it in 2 steps. We first recognize that r perpendicular is simply the radius of the hoop, and that for all masses on the hoop, those masses are all the same distance away. So our capital R is constant for all of our mass elements, so we can factor it out of the integral. So we're going to integrate d theta, and we're going to do so from, let's say, theta equals 0, which might point to the right, and we're going to integrate all the way around to theta equals 2 pi. But we're integrating d theta from 0 to 2 pi, so that integral is simply going to be 2 pi. And here we go. We come with our final result that the rotational inertia for the hoop about its center is mr squared. Okay, so that's fine. What about another object? How about a solid disk, like a merry-go-round? Right. Well, in that case, our object looks something like this. We'll have a solid disk with some height. Kind of like a quarter or a coin of something. Okay, and we're going to assume it's uniform density, and we'll assign it a mass, big M, and a radius, capital R. Okay, and again, if I look at this from the top down, I have the following. And we can think of this solid circle as a collection of small hoops of bigger and bigger radius, right? So again, we're talking about a situation where we're going to rotate about an axis through the center of the disk. So our rotation axis in the first picture might look something like this, right through the center of the disk. In the top view, it would be a line perpendicular to the screen right through that purple dot in the middle of the disk. Okay. So how might we approach this? Well, we still have the case that the rotational inertia for this extended object is given by the integral of r perpendicular squared dm. Okay. This time, our dm is the mass of this whole little ring. Which we might call a hoop. Okay. This hoop is at a distance r from the center, but that r changes from 0 to capital R as you move out and increase the size of your hoop. Okay. The mass of this ring is, we could write as 2 pi r, the circumference of the ring, multiplied by the mass density. Of the ring. What is the mass density of the ring? Well, it's the total mass divided by the total area. Okay. And we actually have to make a little bit of a change here. And we'll say that this little hoop has an infinitesimally thin infinitesimally small width. So we can write the area of that hoop in the following way: 2 pi r dr times this density. Okay. So now we have an expression for dm, which we can use down here in our integral. The integral of r squared now, where r is the radius of the hoop of interest, times dm, which is 2 pi r dr lambda, and lambda is constant. So is the 2 pi. So we factor out the lambda, and we get the integral of r cubed dr, and we're integrating from 0 to capital R because the integral goes from this infinitely small hoop to bigger and bigger hoops until we get to the outer rim, and that is a radius of capital R. We can now use information about what lambda is. It's total mass over the total area of the disk, and we can integrate r cubed, and we get 1/4 r to the 4th evaluated at those limits. We have some cancellation, and we end up with 1/2 m times r to the 4th power evaluated at those two limits, which is 1/2 m r to the 4th minus 0 to the 4th, which is just 0. So we have 1/2 m r squared. So the rotational inertia of a disk with the axis through the center of the disk can be written as 1/2 mr squared. Okay, and you can repeat calculations like these integrating over other shapes, squares, rectangles, spheres in 3 dimensions, and so on, to compute their rotational inertias. We can also look up the table of rotational inertias in the textbook, and I'll provide that for you as well in the future. Okay, so that's it. It's a quick video to see how to calculate rotational inertias of extended objects using integrals in calculus. We'll come back again next time, but until then, take care and be well.